Dear students, a very good morning. Today, the last part of our complex numbers, part 8, I am about to start. In this, we would solve problems on complex numbers. Our first problem is, show that root over I plus root minus I is real. So we start with, let u is equal to root I plus root minus I. We assume this quantity as u is equal to root I plus root minus I, and we will determine value of u. Squaring both sides, we have u square I minus I plus 2 I minus I, a plus b whole square. That is, u square is equal to I and r minus I gets cancelled. U square is equal to 2 root minus I square. That is, the value of u square is equal to minus 2 root minus I square, which may be further written as u square is equal to 2 into 1, since I square is equal to minus 1, minus I square is 1, and square root of 1 is 1, so u square is equal to 2, u is equal to root 2, which is always real, plus minus root 2 is a real quantity. Therefore, the given quantity root I plus root minus I is a real quantity. This is problem number 1. We now move on to problem number 2. If y is equal to root x square plus 6x plus 8, so that one of the values of root 1 plus iy plus root 1 minus iy is root over 2x plus 8. This is again a very common problem in our different examination, and our procedure of determining its value remains the same as the last problem. So I start with, let u is equal to root 1 plus iy plus root 1 minus iy. I have to determine value of u. I have to determine one of the values of u, because I am assuming u is equal to root over 1 plus iy plus root over 1 minus iy. Therefore, after assuming this, I square again, squaring both sides. On squaring both sides, u is equal to 1 plus iy, 1 minus iy plus 2 root 1 plus iy into root 1 minus iy. We would keep our technique of solving problems very consistent. That means using same method repeated again, so that we do not forget how to tackle a particular problem. Here also, after after assuming u is equal to root over 1 plus iy plus root over 1 minus iy, I square both sides. And on squaring both sides, what I find is that these two get cancelled and left over is u square is 1 plus 1 is 2 plus 2 root over 1 minus I square y square. I square is equal to minus 1, so 1 plus y square. Therefore, after multiplying this, 1 plus iy into 1 minus iy is 1 plus y square because I square is equal to minus 1. So therefore, I further write this as u square is equal to 2 plus 2 root under 1 plus. Now our y is equal to root over x square plus 6x plus 8. And when I place y square is x square plus 6x plus 8. I repeat this once again. I am substituting y square. What is y square? Y square is x square plus 6x plus 8. I replace it here. So therefore, my u square is equal to 2 plus 2. And this is nothing but x square plus 6x plus 9, which is nothing but x plus 3 whole square. This quantity is x plus 3 whole square. Therefore, u square is equal to 2 plus 2 root over x plus 3 whole square. See the technique. After multiplying this 1 plus y square, what is value of y square? Y square is squaring this x square plus 6x plus 8. And that value is when replaced. That gives you 2 into root over x square plus 6x plus 9. This is nothing but x plus 3 whole square. On squaring and cancelling this radical sign, I have u square is equal to 2 plus 2 into x plus 3, which is equal to u square is equal to 2x plus 6 plus 2 is 8, and u is equal to root over 2x plus 8. I am neglecting negative sign as the question says one of the values. One of the values is this, the other value may be minus, but I am not concerned. Our concern is only this. So u is equal to root over 2x plus 8. This is problem number 2. I hope you are understanding this problem. Try to work them repeatedly many times so that you are in control of these types of problems. Our problem number 3. If z is equal to x plus iy and mod z minus 1 plus mod z plus 1 is equal to 4, determine the locus of z in complex plane. This is our problem number 3, and here you find that problem involves locus also. There is involvement of locus also. This is a this is the given condition, and I have to find locus of the complex number Z. So I start with Z as Z is equal to x plus iy. Z minus 1 is x plus iy minus 1. Z minus 1 x minus 1 plus iy. More Z minus 1 is x minus 1 whole square plus y square under root Z minus 1 more whole square is x minus 1 whole square plus y square, equation number 1. I substitute value of Z and then determine Z minus 1. Z minus 1 is x plus iy minus 1. Real part, imaginary part, modulus already discussed. So, modulus of Z minus 1 whole square is equal to x minus 1 whole square plus y square. Then our second case is Z plus 1 whole square. Z plus 1 is equal to x plus iy plus 1. Z plus 1 is equal to x plus 1 plus iy. More Z plus 1 whole square is equal to square root of x plus 1 whole square plus y square. On further simplification, mod whole square, therefore, on further simplification, z plus 1 whole square is equal to x plus 1 whole square plus y square. This is equation number 2. As we have equation number 1, this is equation number 2. Now, from 1 and 2 and 2, we have x minus 1 whole square plus y square, x plus 1 whole square plus y square is equal to 4. This is our given condition. I am using this. I am substituting value of both of them from 1 and 2. From 1 and this is 2. I substitute their values. And on further simplification, x square minus 2x plus y square plus x square plus 1, 2x plus y square is equal to 4. Minus 2x plus 2x gets cancelled. X square plus x square is 2x square. Y square plus y square is 2y square. And 1 plus 1 is 2 minus 4 is equal to 0. That is x square plus y square is equal to minus 1 on simplification. I have simplified and cancelled 2. What is the result I am getting? My result is x square plus y square is equal to 1. Which this is a circle with center 0, 0 and radius is 1. So therefore, as far as problem number 3 is concerned, value of z is given x plus iy and an equation is given mod z minus 1 whole square plus mod z plus 1 whole square, which is equal to 4. And I have to determine locus of z in this particular complex plane. I start off with z. I determine value of z minus 1 whole square. I determine value of z plus 1 whole square. The writing pattern should be this as we are following. We are mentioning equation 1. We are mentioning equation 2. Then how do we use 1 and 2 in the given equation? And on further simplification, we get our required result. After you obtain locus, define what is the locus, whether it is a circle, whether it is a conic section, that is ellipse, hyperbola or parabola. You have to define it. And after defining what the locus is here in our problem, it is the circle. And if it is a circle, what is its center? Center is 0, 0. What is its radius? Its radius is 1. When you work problems on circle, you come to know how to determine center and radius of a circle. Or rather, which equation represents a circle, which equation represents other conics. So therefore, for the time being, you may write this down, and later, once you start with circling or analytical geometry, then things will be much more clear. So therefore, this is problem number 3. We are now moving to problem number 4. Problem number 4 says, if z is equal to x plus iy and mod z is equal to 1, show that z minus 1 by z plus 1, z not equal to minus 1 is purely imaginary. Quantity. This is a very important problem, and in our examinations, whether half yearly or annual, or in central examination of class level, these types of problems are there concerning locus, concerning totally purely and imaginary quantity. Now, how to work this out? What are we given? We are given two conditions. What are they? First, our value of z is given, which is the complex number x plus iy. And when this complex number is given, and at the same time, this complex number is such that modulus of it is 1. So I start with the unit condition as mod z is equal to 1. It implies root over x square plus y square. That implies this is our very important given condition. We will utilize this. Now, x square plus y square is equal to 1 is condition 1. You may mark. I am also showing you the writing style also, how to proceed with the problem. That is very important. Now, I start with z, and now z minus 1, z plus 1 is the given quantity of which I have to show that it is purely imaginary. It is not real. It is purely imaginary. I substitute value of z x plus iy minus 1, and in the denominator also x plus iy plus 1. Use these brackets. Use these brackets. So therefore, this is equal to x minus 1 plus iy. This is third bracket. And in the denominator, x minus 1 plus iy. I multiply immediately by the conjugate of the denominator. By the conjugate of the denominator, x plus 1 plus iy is a complex number. Its conjugate is x plus 1 minus iy, which I am multiplying numerator as well as the denominator. Both in numerator as well as in the denominator, I am multiplying. So my denominator is equal to x plus 1 whole square plus y square. X plus 1 whole square plus y square is the denominator, and in the numerator I have this into this is x square minus 1. This into this is minus iy x minus y. And similarly, when I multiply with this iy x plus 1, and when you multiply these two, it is equal to plus y square. On further simplification, x square plus y square minus 1 minus iyx plus iy plus iyx plus iy. And I have written this y square out here, and in the denominator it is x plus 1 whole square plus y square. I cancel out these two, and what is left over is x square plus y square minus 1. This is the real portion. And what is the imaginary portion? Imaginary portion is 2iy. Therefore, x plus 1 whole square plus y square. From 1, this particular condition, I apply it out here. This complex number reduces to 2iy by x plus 1 whole square plus y square, which is an imaginary quantity. Because the real portion is equal to 0. When real portion is equal to 0, only imaginary portion is remaining. And when imaginary portion is remaining, no real number, so therefore it is purely an imaginary quantity. A quantity which is on the y-axis of the arcade plane. The x portion is 0, 0, 1, 0, 2 are all on the y-axis. So therefore this is an imaginary quantity where real portion is equal to 0. This is problem number 4. So therefore this is problem number 4. We would now work on problem number 5 in the next session. Thank you.